Hi, welcome to Fundamentals Friday. This one comes from a forum post from a user named Laurie. Thank you very much, Laurie, for asking this very interesting question. Why do you parallel electrolytic capacitors? You do a teardown of a product, you open up and you see multiple electrolytic capacitors in parallel. It's quite common to actually find this thing in power supplies and all sorts of applications. Why do we do it? There's actually quite a bit to it. Let's take a look. Now, I will just stick to what Laurie asked here, specifically about electrolytic capacitors. I won't go into, for example, you often see you'll have a 100 nanofarad in parallel with a 10 nanofarad in parallel with a 1 nanofarad across bypassing, say, a modern FPGA, for example. That's a different thing entirely, and I have covered that before. So we'll just take a look at electrolytic capacitors, generally in power supplies like this and other sort of big higher power applications. Now, you might typically see these paralleled electrolytic capacitors in, say, your standard linear power supply. We've got a AC transformer, full wave bridge rectifier, and then you might see more than one. Sometimes you'll only see one, other times you might see 2 or 3 or 5 or even 10 in some sort of extreme example. And also you'll see them in, for example, DC to DC converters like this. So we've got DC in, we've got DC out, whether or not it's a boost or a buck, step up, step down, doesn't matter, but you'll typically see generally a couple of electrolytic capacitors on the output. You could also see one, but it's fairly common to see 2 or 3. Why? Why not just use one? Well, basically, when you design a circuit or a product, you're going to have a whole bunch of specs you're going to meet. At least if you design it properly. I mean, you can't just go, oh, I'll just bung in a 100 mic cap, she'll be right, no worries. But if you actually design it properly, you could have a whole bunch of specifications for your electrolytic capacitors here. Some of them can include, well, the main one, of course, is generally going to be your capacitance value. It could be 100 microfarads, for example, could be 1,000, 10,000, whatever. You're going to have a maximum ESR value, for example, 0.1 ohms. That's very common in DC to DC converters, for example. For stability, they need either a minimum, maximum, or sometimes like a window where the ESR, you have to get the correct ESR, which is the equivalent series resistance inside the capacitor. Because remember, capacitors aren't ideal. You have to deal with the real world where your typical capacitor like this actually has an ESR in here. This is the equivalent series resistance in there. It's going to have a certain resistance value. It can depend on the frequency and all sorts of complicated things. Then you're actually going to have the capacitor itself, the ideal capacitance in there, and then you're going to have a little bit of lead inductance as well. Quite a complex little beast, your practical capacitor. There's no avoiding this stuff. So you typically read your data sheet for your DC to DC converter and it might say you need a certain amount of capacitance for that particular load, maybe either a minimum, maximum, or a window of the ESR value. So you've got to meet that. The other main thing is size. You don't have an infinite amount of room inside modern products. Sometimes you do. You've got the luxury of, space isn't a problem. But with today's miniature modern electronics and everything else, be it surface mount or through hole here, everything we're talking about is going to be applicable to both surface mount and through hole electrolytic capacitors. But yeah, you might have to meet a volume envelope. Typically, height is a major requirement for capacitors, and well, it can go into, you may be forced to use several different ones because of different height restrictions. Then you've got cost restrictions, for example, which we'll go into. That may be a reason why. And then you have operating life as well. There's quite a few specs in here, so let's go through all the reasons. I think we'll find quite a few why you might want to parallel electrolytic capacitors instead of using just one. So I've come up with a list of 9 different reasons why you might want to parallel capacitors, and they're all going to intermix. As you'll see, there might be one specific reason or a combination of reasons that push you towards either using a single capacitor, nothing wrong with using a single capacitor if it meets all your requirements, or as the question asks, why do we parallel them? Let's find out. Now, some of them have been copied from the specs over here, and we'll talk about them in more detail, but there's at least double the number of reasons in here. Whoa, let's take a quick look. Hopefully quick. Now the most obvious one, of course, is your capacitance value. Take, for example, your linear power supply here. You've got a full wave bridge rectifier, so we're getting a 100 hertz typical full wave bridge, as you should be familiar with, standard building block circuit. Well, we have to generally meet a ripple voltage requirement on here. So if the black one there is the output of your bridge rectifier, your capacitor is going to smooth that, and depending upon your load, is going to be dependent upon how much ripple you actually get there. And it's basically dependent upon three things: your load current, your capacitance, and your frequency. Your frequency, of course, here in Australia, 50 hertz mains voltage. Your full wave bridge rectifier doubles it, going to have 100 hertz, for example. So it's only dependent upon your load value and your capacitance. The ESR and stuff doesn't really come into it. Well, it kind of does, but let's not go there. This is like a just a rough rule of thumb formula that you can use to calculate your ripple voltage. So you might be using a 7805 voltage regulator. It drops out at 7 volts, for example. So you don't want your minimum ripple current there to be under a certain value. So you got to have a certain amount of capacitance. You plug the numbers in and you figure out, okay, I need 1,000 microfarads of capacitance, for example, to give me my required ripple current. Now, of course, you can just stick in one capacitor of 1,000 microfarads and Bob's your uncle, right? You've done the job. Okay. In this basic example, that might work, but there's a whole bunch of other stuff which could influence your decision to use more than one. Now, the first one, of course, might be physical size. You might only have 10 millimeters height available, but you need 1,000 microfarads at, say, 15 volts or something like that. So you look through the catalogs and data sheets and you find that, well, it's really quite difficult to get a cap that meets that physical height requirement. So you might have to go for a shorter cap. So you might only be able to get, say, 330 microfarad 16 volt cap in the height you want and the diameter you want and everything else. So, hey, bingo, you have to use, it might force you into using 330 mic capacitors. Mic is short for microfarad. Capacitors in parallel instead of one 1,000 mic cap. Obvious. So we've covered two things, capacitance and physical size. Well, what about cost? Well, once again, you look through your DigiKey catalog or whatever, wherever you're sourcing your parts from, you might find that, hey, the 330 microfarads at 16 volts might be cheaper than the equivalent 1,000 microfarads at 16 volts, for example. So, hey, you might go just on cost reasons alone if space wasn't an issue or whatever. That could be your driving factor. Who knows? And another big one, BOM reuse. BOM is bill of materials. You might find elsewhere in your design you're already using a 330 microfarad capacitor, for example. So, well, why specify another 1,000 microfarads in your bill of materials if you can get away with just reusing 3 of the ones you already use? And if they're surface mount, for example, you can buy them all on one big ass reel like this, which is much more economical. These are 220 microfarad 16 volts. So if you're already using these in your design, hey, you get a bulk price and you only get to take up one of the feeders in your pick and place machine. Beautiful. That can be reason enough to use multiple capacitors. Another one that might be important for specific products is product configuration. Let's say, for example, you had an audio amplifier, okay? It needs a big DC voltage rail with lots of bypass caps because it's, 100 watts per channel or something like that. Well, let's say you had two models that had, one was 50 watts and the other was 100 watts. Well, the amount of filter capacitance you're going to need is going to change depending on the model. So you might lay out your PCB to have the multiple footprints for the capacitors, and you might only populate the number that you actually require. You might have one or two in a particular design, and then you might have 4 for one that has twice the power or something like that. Now here's a big one which has an impact on many different reasons here. This is the ESR, the equivalent series resistance. As I showed before, the model of a capacitor is the ESR in series with the capacitance itself, in series with a bit of lead inductance, and there's some other little niggly stuff in there we won't worry about, like leakage resistance and dissipation as well. But what we're concerned with is this ESR here. Now, if we take the case of a 100 microfarad capacitor that's got 0.1 ohms ESR, for example, that is equivalent, you can build that same capacitor up by putting two capacitors in parallel of 50 microfarads each. Of course, that's not like a preferred value, so you choose like 47 mic, near enough. Electrolytic capacitors are typically like plus minus 20% anyway. So yeah, near enough. Anyway, these can have a 0.2 ohm ESR, which means that they can be smaller because the ESR is going to be pretty much determined by the physical size of the capacitor. So the larger the capacitor for the same capacitance, typically the lower the ESR. So you can get away with two smaller capacitors in parallel of a higher ESR figure, and that's equivalent because they act like parallel resistors. So you just use your standard parallel resistor formula, you get 0.1 ohms and total. They're exactly equivalent. But apart from the size issue, where this really matters, and we get in a couple of things down here, the ESR, of course, it's a resistor. When you pass current through it, in this case ripple current that we saw before, especially in high power sort of applications, you can get, you know, a lot of current, like amps or something like that. You're going to get power dissipated in that equivalent series resistance inside the capacitor body itself. That little aluminium cased electrolytic capacitor is going to heat up internally due to the power dissipated in the ESR. In an ideal world, in an ideal capacitor, there would be no power dissipated, but doesn't work like that in the real world. You're always going to get some form of power dissipated inside that capacitor. And the reason that temperature rise matters is because aluminium electrolytic capacitors are filled with a dielectric liquid which essentially can dry up the higher temperature they get. They have a finite life. I've done many videos on this. You know, the capacitor plague, for example, bad capacitors, typical failure mode inside, typically a high power product like a television or something like that, gets quite hot in there, use a lot of power, you need a lot of capacitance, and they all get hot internally, and it can shorten their life. And typically all you need to do to fix a product might be just to replace the capacitors because the dielectric has dried up in there. They've got a finite life. Take a look at this data sheet, for example, of a typical Rubicon capacitor here, and you'll see that they can have anywhere from, say, 4,000 hours life up to, say, 10,000 hours. The larger the voltage rating of the capacitor, typically the longer the life, the bigger the diameter, the longer the life, all that sort of stuff, because they don't heat up as much internally, the physically larger capacitors. So this is going to make a huge difference to your product. And you'll notice down in the table down in here, you have different ripple current ratings for different size and values and voltages of capacitors, and that ties into the life up here where it tells you that it's going to have X, 1,000 hours life at 105 degree C rating is a typical high temperature capacitor. For example, they typically come in two temperature grades, either 85 degrees Celsius or 105. You can get slightly higher than that, but they're the two major ones, and it's going to have a rated life based on a certain temperature, and that's all determined by your ripple current, your ESR, and everything else. And of course, a specific size of capacitor is going to have a specific ability to be able to dissipate that internal heat, and roughly it might be equivalent to the outside surface area of the capacitor. For example, just ignoring like internal construction and things like that. So for a typical cylindrical radial capacitor like this, we'll have an area determined by the outside of the capacitor, and then we'll have the area on the top as well. And your typical formula is area of a circle is pi r squared, and then the outside layer of the aluminium casing is going to be pi times the diameter times the length of the capacitor, i.e. the height of the capacitor, and you can add those together and you've got total surface area. And for those really keen, you could go into all the thermodynamics of it and how to actually attempt to calculate and model temperature rise of the capacitor. It has to do with, do you have any airflow over it? Is it radiated? Is it in a sealed enclosure? How can it radiate to the air inside, and then how does it radiate outside the case? And thermal calculations like this, very ugly, very complex. But generally, the more capacitors you have, the greater the total surface area you're going to spread the ESR across. Remember, in this case, we had two separate capacitors of 0.2 ohms ESR each. They're going to share the current, they're going to share the power dissipation between them. So you're going to end up with typically a longer life than your single capacitor with equivalent electrical specs. So your longer life here can be a major reason for having multiple capacitors in parallel. Might be the only reason to do it, and you might have done the calculations to figure it all out, or you might have gone, well, this product needs to be reliable, it's industrial, it's in a hot environment, for example, so the temperature rise inside the capacitor, of course, is going to be above ambient. So if you design your product to work up to 50 degrees Celsius, then you've got a design margin on top of that. If you use an 85-degree caps, you can calculate the ripple current and the temperature rise inside, or typically you might do empirical measurements, actually put a thermocouple and use a thermal camera, actually get some temperature measurements on the prototypes, for example. Is it good enough? Then you can calculate, are the capacitors going to be the Achilles heel in the reliability of your product or not? And you might decide to spread it across 5 or even 10 capacitors, something like that, because in this case they just all parallel up. So if we wanted to go to the extreme and say use 10 capacitors, we'd use 10 microfarad capacitors with 1 ohms ESR each could give us the equivalent capacitance here. And in that case, each of the 10 capacitors is only dissipating 1/10 of the power. So depending on the thermal performance of the thing, the temperature rise is going to be very small compared to a single capacitor. So you might have increased your lifetime by several orders of magnitude. Now, another big thing is redundancy. Okay, if you've got a single cap, then you've got a single point of failure. If that capacitor fails, you've just got, you're not going to be able to filter your power supply anymore. Your DC to DC converter is going to go crazy, whatever, and your product's going to muck up. But if you had, say, 2 in parallel like this, well then one, if due to, say, manufacturing reasons, you could have a defective cap or something like that, then, well, the other one might be able to take over if you're designing sufficient engineering margin into there. So you've added redundancy to your design just by adding an extra capacitor in parallel to take it out, because capacitor failures heat up. It's sort of like a snowballing type effect. The more it heats up, the more the dielectric dries out. As the dielectric material inside dies out, then the ESR goes up, and the ESR goes up. It's going to dissipate more power, and it's a snowballing thing. And these capacitors can start to fail very quickly. But if you have multiple capacitors in there, you can add a bit of redundancy to your system just to ensure reliability. You can see how it's all starting to come together, all these many factors to determine reasons why you might or might not use multiple capacitors in parallel. But generally speaking, it's a pretty good idea to do 2 if you're designing a reliable product. Now, last and maybe least, or it depends on what sort of requirements you got, are the peak current considerations. Now, if you have 1 capacitor, for example, and 1 load, let's say we just have 1 capacitor. This is looking down onto our PCB. We're talking about physical PCB implementation here. So the red, just imagine these 2 capacitors don't exist. You've got 1 capacitor here, it's driving the load, then all of the current, including peak currents, has to flow through that particular trace. And depends on your, on really high power designs, you can get a lot of loss in those PCB traces. But if you went for 3 capacitors in parallel, for example, you wouldn't just wire them straight here. You might have a separate trace going to the load like that. So you share current through each particular trace, so you can have smaller traces, less drop, going to a specific star point over here at the load. So you're going to have a current flowing through this trace, this one, and this one, which will be 1/3 the current you would have with only 1 capacitor, and then you would get smaller voltage drops across there, Ohm's law, because we're going to have a certain PCB resistance depending on the thickness of your copper. Typical 1 ounce copper, for example, you're going to have a voltage drop as small as it might be. It can, in big high power systems, this can be a real consideration. So now you've split your current up 3 times like this, you're going to have much smaller voltage drops, and your load's going to be much happier because you've used multiple capacitors in parallel. So you might have physically implemented them as 3 separate capacitors like that, but on your schematic, you're just going to show them as 3 like that. But typically, if you're a good designer, you'll have a note on your schematic like that, explaining to the PCB layout person, which might be you because you might forget, explaining to lay it out in this sort of configuration because it's important. And a different configuration yet again, well, you might dedicate one of your capacitors, for example, to another load out here, just so that you don't have to share the same copper here, because if this load here is a pulse load, for example, and it's pulsing, then, you know, physical layout of your PCB and your traces matter. You don't want that tied onto here, because if this load here, you know, takes a big gulp of current, then you're going to get a voltage drop and a droop on your traces go into this load over here, which may not like it. So you might actually show them, once again, electrically all in parallel like that, but physically going off to a different load. But, you know, if you were, once again, you'd put a note there, but if you're a good you're good at drawing schematics and drawing them cleanly, then you'd put that capacitor over against the load on the specific part of the circuit. But hey, you might see them drawn like that, and they physically might be right next to each other, but you might actually lay out the traces differently. And it's not just the internal ESR of the capacitor either that heats up the thing. You've also got connection losses as well. The leads on the capacitor, for example, they've got a certain amount of resistance, your solder joints, everything else, that can propagate. They're going to heat up at large currents, for example, even though resistances of the lead wires are very, very small, right? In large high power applications, it's going to matter. That's why some really, really big caps don't have just leads, pins sticking out. They have gigantic lugs on them and big mounts that, you know, you bolt them down to the PCB and everything like that. So, you know, it's a really high current, it's a really big deal, and you might have to use proper crimp cables to go up to them in real, you know, if you open up really high power amplifiers and things like that, they may not just have a couple of leaded radial capacitors stuck into the board. It can be a real big deal. So is those interconnects, of course, they have a certain amount of resistance. I squared R losses, they're going to heat up as well. They can conduct the heat into the capacitor itself, and that all contributes to the internal heating of the capacitor. So it's not just the ESR, but there's a whole bunch of other factors. So when you split capacitors like this, you're also sharing the interconnect, the connection losses between the multiple capacitors, and that can make or break your design. So there you go. I hope I've answered Laurie's rather innocent question. Why do they put multiple electrolytic capacitors in parallel? And I easily came up with 9 different reasons to actually do that. And as you saw, they can all intermix together, and you may only use one of these, maybe, you know, a deal breaker. Right, I've got to use multiple capacitors because of cost, or because of BOM reuse, or might be some sort of, you know, weird ESR requirement. It could be some big physical load requirement. It could be longer life, redundancy. That's a very popular one. In fact, that's probably one of the most popular reasons. As I said before, if you're going to design a product and you want it to be reliable, and you've got a capacitor in your power supply, and the load is, you know, there's a reasonable amount of load, and you might check how much ripple current you get in, and, you know, all that sort of stuff, especially on DC to DC converters, for example, where peak ripple currents can be very high. Well, you know, one capacitor may not cut it. What if you get a faulty one out of the batch? Not so good. Then, hey, put some extra capacitors in parallel for redundancy. Now, it's actually quite hard to show a lot of this in practice on the bench, but I've got one little bench example where I'm going to show you how we can actually spread the temperature rise among capacitors by having multiple ones in parallel. Let's check it out. Okay, what I've got is a simple variaboard here with one capacitor and then 10 capacitors, and we'll see the difference between the heat rise in these things. Now, one is 100 microfarads, 50 volts, and the other is 10 microfarads at also 50 volts, and yes, they're exactly the same Rubicon brand. I'll link in the data sheets down below so that you can have a look at it if you're keen. Now, I've got this powered from an AC transformer over here. It just allows me to select the voltage. We've got a diode bridge rectifier there, full wave bridge rectifier. I'm actually powering them both at once, and you'll see why in a second. And so I've got just another additional diode isolator there, and just some probes on there so that we can probe the ripple voltage on this thing. And I've got the outputs here So we've got a standard full wave bridge rectifier, and then I've got two constant current dummy loads, my do-it-yourself one, which is seen in a previous video, and the BK Precision one here. And this will allow us to set a constant current load so that we can get a nice big ripple value on both of these capacitors. So both are 100 microfarads, except this one is made up with 10. And of course, the total surface area here is going to be a hell of a lot more than the surface area here. So yeah, we should see a temperature difference, and we're going to have a look at that with our FLIR E8 infrared camera. Let's go. Now, I don't currently have anything powered on. You can see that our temperature range is only small, like 4 degrees Celsius difference. You might be able to see in there some difference in the temperature on the rear capacitors over here. And that, watch this, I haven't got it turned on, but look at that. I'm adding my hand in here. This is actually reflection off my hand down off the metallic tops, the aluminium tops on those capacitors, and it's reflecting back. So you've got to be careful when you're doing thermal measurements like this to make sure you're not actually getting heat reflected, and you've got to set up the emissivity correctly, and yeah, and the bright aluminium tops on the capacitors isn't the best thing. But anyway, so we could like paint the top of the capacitors black or something like that if we wanted to. Anyway, so you just got to be careful to block out any reflected heat. I'll show you that. Look, I'll put my hand here, and you can see the heat, and I'll put a book in between. Boom, gone. Now, please forgive me. This is going to be really tricky to get in one shot, but I wanted to power this up and like from cold and show you. So you can see there's hardly any temperature differential in there at all. You can't see much. Now, if I apply power to the thing and then apply it, so I'm going to feed in 15 volts AC. Here we go, and I'm going to, you can see that the bottom one, you can see the diode heat up there. Now I'll cover that in a minute because that's going to affect our temperature range, but you can see that I've got 200 milliamps on the single 100 microfarad capacitor. That's the one down the bottom here. This one down here, I've got to be careful not to touch anything, otherwise, yeah, you can see it probably starting to warm up. Actually, I should do the other one, so I'll set the other one to 200 milliamps as well, and bingo, now we're drawing 200 milliamps from the top one, and you can see that, but you can see, look, you see the 100 microfarad capacitor starting to warm up. So what I'll do is I'll cover this. I've got to, actually, that was probably bad, I was touching it for too long, damn. Yeah, that post-it note. Anyway, I'm trying to cover up those diodes so it doesn't affect the maximum range of our reading there, but you should be able to see after a while it's going to ramp up. Now, the important thing to note here is that our conditions are identical, because what do you want when you have a simple full wave bridge rectifier circuit like this? You want to, all you care about is the ripple current, okay? And you can see I've got channel 1s and channel 2 in there, and they're the same ripple current. You can see that right in there. I mean, this is really extreme, okay? Because I want to be able to heat these caps up. This is not normal design, you know, that we're doing here. You wouldn't have 13.6 volts peak to peak of ripple there. That's insane, with the lower voltage there of 10 volts. Remember, we're 5 volts per division there. So they're both identical. So we've got 10 capacitors, 1,000 microfarads, as we saw in that basic rule of thumb formula before. The ripple voltage is just going to be dependent upon the frequency and the load current. The load current is the same for both of them. We've got basically the same 100 microfarad capacitance for both of them, so we're getting the same ripple. But you can really see that bottom one heating up compared to the top ones. I'll get a closer shot on that. We've only been like powered up for less than 5 minutes. Okay, now I've replaced that post-it note there with a big aluminium shield, and here's my pointer coming in here. You can see the scale change dramatically, but we're not talking about a big temperature difference here. I mean, it's showing that the maximum that cap's getting to is basically 27 degrees, but it's a lot. But that is like, you know, a good like 5 degrees more than the other caps, which are all sitting around ambient, you know, like sort of not far above ambient temperature, just a degree or two. So you can see the temperature spread between these things, let alone the core temperature inside, because you start getting into the the thermal properties of the capacitor and how it can get its heat out and things like that. It's like a semiconductor die. The die temperature inside is always going to be hotter than the case temperature, for example, and then the heatsink less than the heatsink temperature. You're going to have losses along the way, but you can see how that capacitor gets much, much hotter, and it's exactly the same ripple current, exactly the same design conditions. Oh, please excuse the light popping in there, but you can see that the capacitor's at the top only like less than 25 degrees, so it's not too far above the ambient in here, but the single 100 mic capacitor down there is like 27 degrees. It's a good few degrees warmer, and if we leave it there for longer or we use higher currents, and this is just designed to show the difference, but I think that quite dramatically shows the difference, how you can actually shorten the life of these capacitors, because as I said, it's a snowball effect. And hey, if you've got a high ambient temperature, this is just like free air here in the lab. It'd be cooler again if I actually turned on the aircon. These top capacitors might actually be more efficient because there's more surface area. So when you've got airflow, even just here in the lab with just the aircon on, a tiny little airflow can make quite a significant difference to the temperature. Or if you're designed into your product and your product's got proper thermal design with fans and everything else, then having all that huge surface area on those 10 caps can be a hell of a lot different to this single 100 microfarad cap here. Now, if you were sufficiently keen, you could attempt to calculate the temperature rise of the capacitor, and you could probably do this using the Stefan Boltzmann law. This is the thermal energy that is radiated per second per unit area. So there's the basic equation, which you can slightly rearrange to get your thermal energy radiated from a hotter object to a cooler object. In this case, it'd be ambient or whatever environment you've got. So what we've got is the emissivity of the material here. So you'd have to go look that up. And then, of course, the capacitors like wrapped in that plastic wrap and things like that. And it gets very complicated. But anyway, the emissivity of your radiating material, i.e. the capacitor, multiplied by the Stefan Boltzmann constant, that's some weird-ass funny number you learned in physics, and multiplied by the total surface area. And this is the big thing that makes the difference here between having 10 caps in parallel with a massive surface area compared to just one capacitor, for example. And then you multiply that by the fourth power of the temperature of the capacitance minus the fourth power of the ambient temperature. And of course, you could rearrange that formula to get the fourth power, well, to get the temperature of the capacitor after letting it stabilize and all that sort of thing. But it's not going to be that easy. But hey, for all you nerds out there, go for it. See if you can do it. Bit of homework. So there you go. I hope you enjoyed that rather lengthy look at why do you parallel capacitors, and that seemingly simple subject like that turned into like a half-hour epic. Sorry about that, but yeah, anyway, there is a lot to it. Even like basic things like this in electronics, you can go to town on these sorts of things and the reasons behind choosing certain things. So anyway, if you want to discuss it, jump on over to the EEV blog forum, and as always, if you liked it, please give it a big thumbs up on YouTube, and you can leave comments all over the place, and yeah, stalk me on Twitter and all that sort of jazz. Catch you next time.